Welcome back everyone. In this lecture, we will continue with the isomorphism theorems. So, now we will see actually the third isomorphism theorem. So, that is about quotient of quotients. So, here is the fundamental question. Okay, this quotient, the notion of quotient groups. Okay, so they are actually giving us many interesting new families of groups. Okay, but one can ask, okay, what's about if you start with the quotient group and then take, okay, some normal subgroup of that which will look like another quotient, okay, then what will happen to like quotient of quotients. So, whether you get anything new from this procedure, like whether you get some new groups, okay, or the new constructions, let us put it that way, new groups in the sense, is it a new construction, but indeed it is not actually a new construction, it will be again some other quotient group. Actually the second derivative will not give anything new. Okay. So, let me just first formulate, then it will be clear what I was actually talking about. So, here so let us recall, okay, again we denote G be a group. Okay. Now, let us say G has actually two subgroups, both are let us say normal, and one subgroup is contained in another subgroup. Okay. So, let us take some situation like this. So, let me draw it using the diagram again. So, you have G and then let us say you have H and then you have N. So, N is subgroup of H and H is subgroup of G. Assume both N and H they are normal in G. So, this is the assumption. So, this is the assumption. Okay. So, now we can actually consider various possible quotients. Okay. So, what one can do, for example, like one can take this G modulo H, G modulo N, and one can actually verify that N also will be normal in H. So, one can take H modulo N, and we want to actually see whether one can compare these quotients or not. Okay. So, that is the thing. So, indeed what we are going to prove, okay, with this hypothesis, okay, let me state the theorem. So, this is the third isomorphism theorem. So, as before, let G be a group, okay, and N subset of H subset of G or the normal subgroups. Of G. Okay. So, then what we have? We have an isomorphism of the following groups. What it is? So, first what you do? You take G modulo H, which makes sense. So, then that is isomorphic to G modulo N modulo H modulo N. So, this you can remember it as like cancelling N basically. Okay. So, when you take this group, okay, G modulo N, so there are so many things are hidden in this statement. Okay. So, for example, first of all, H modulo N makes sense. So, what is the meaning of that? So, that means N is normal in H. So, that is the first observation. The second observation, so in particularly H modulo N can be treated as a subgroup of G modulo N, and this is again normal in G modulo N. So, then only we can actually make this quotient. Okay. And H is already given to be normal in G. So, then once we have these two observations, then we can make this G modulo N modulo H modulo N. We are saying that this quotient of quotient is again a quotient. Okay. So, when you go to the second iterative, that is when you consider this quotient of quotient, you are not getting anything new, you are getting only the quotient. Okay. So, it is very powerful result. So, let us verify the hidden statements first, okay, these statements, and then later I will actually prove that this is. Again this isomorphism also will come from the first isomorphism theorem. So, first isomorphism theorem in a way it is the mother theorem for all isomorphism theorems. So, all other isomorphisms can be only proved using first isomorphism theorem. Okay. So, let us see the proof. So, what is given? Let us recall n, h, they are normal in G and n is subgroup of h, that is all given. So, this is given. So, now what we want to verify? Let us verify that n is normal in h. Okay. So, how do we verify? Let us take some x in h and look at x n x inverse. But n is normal in G. So, x n x inverse will be n, okay, as x is in G and n is normal in G. So, that proves that n must be normal in H. So, this is verified. So, this is in some sense obvious because n is normal in G. So, normalizer of n in G will be G and H is just a subgroup of actually this normalizer. So, if you go back to that B being normal in AB that I proved in the last class, you can see that this NH is exactly H. So, N is normal in H. Okay. So, this is something we already verified. So, what is about the second statement? So, now it makes sense H modulo N is normal in G modulo N. Sorry, H modulo N is a group, that makes sense. Okay. So, now if you think about it, what is G modulo N? G modulo N is nothing but all left cosets of N in G. Okay. So, in particularly we can think of H modulo N as a subset of G modulo N, no issue. Okay. But this is something we already verified. If you have a group homomorphism from G to G dash, if you take H to be a subgroup of G, then if you look at the image phi of H inside G dash, so this is also a subgroup. If you start with the subgroup and if you take image of a subgroup, that must be subgroup. In particularly, you have this quotient map pi from G to G modulo N. Okay. Then it is not hard to see, okay, this is mapping x to x n. So, then pi of capital H will be just H modulo N. Okay, this will be all those x n where x is coming from capital H. So, using this result which we proved already, okay, this is something we proved already. So, using this we can see that pi of H, which is H modulo N, is a subgroup of G modulo N. Okay. So, H is being subgroup of G modulo N is obvious. Okay. So, this is fine. We want to verify H modulo N is indeed normal in G modulo N. So, this is also something I gave it as exercise, but let us verify it here. Okay. We want to verify H modulo N is normal in G modulo N. So, how do we verify? Start with some element, let us call it Gn inside G modulo N. So, let this. Now, consider, okay, so what we need to verify? Gn H modulo N and then Gn inverse. So, this is supposed to be subset of H modulo N. So, that is what we want to verify. So, there is another way to verify this. Okay. This is something I will leave it to you to check directly. Okay. So, this is something I do not want to do directly. Okay. So, if you take the conjugate of this H modulo n with respect to G modulo n, then it must be subset of H modulo n. Write everything in terms of cosets, then it will become clear. But what I want to do, I want to actually realize H modulo n as kernel of something, so that it becomes clear it is a normal subgroup. Okay. So, let us see what will be the map that one can define, and then how to prove this is actually kernel of something. So, here is the natural map. Okay. One can take G modulo capital N and then map to G modulo H. Okay. So, what is the map that I am going to define? Let me call it okay, F again. What is this map? You take this coset Xn and then send it to Xh. Okay. So, note that we need to verify whether it is well defined or not, because here on the left side you may have two representatives, because you have used the representatives to define this map. X in Xn may not be unique, okay, there could be something else. So, that means Xn can be equal to Yn. So, then we need to check. So, this is something we need to check, then that will imply Xh equal to Yh. Okay. But what is the meaning of Xn being Yn? So, this means X inverse Y is in capital N. Okay. This is actually if and only if, this is something we verified. But that implies what? That implies X inverse Y is in capital H, because N is subset of H. Okay, that is the given hypothesis. N is to begin with is a subgroup of H. Okay. So, that means this X inverse Y is in capital H. So, but that means what? That means if you take XH is same as YH. Okay. So, that proves that this is indeed well defined. So, F is well defined. Okay. So, now you can easily see that this is a surjective map, because any coset here in G modulo H looks like some XH, and obviously you take Xn and map it to XH. Okay. So, it is well defined and surjective. So, these two things are obvious. Now, we need to check whether it is a group homomorphism in order to use the first isomorphism theorem. So, how do we verify whether it is a group homomorphism? Let us write down what it means. You take f of x1 n x2 n, then you have to say that this is same as f of x1 n f of x2 n. Okay. But what is x1 n x2 n? So, that is exactly x1 x2 n, because n is normal. Okay. So, then what is f of x1 n x2 n? So, that is going to be f of x1 x2 n. So, which is exactly x1 x2 h. But on the other hand, okay, on the right hand side, what we get? F of x1 n f of x2 n, which is x1 h times x2 h. Okay. But h is also normal in G. So, then this becomes equal to x1 x2 h. So, that means these two are equal. So, these two are equal. So, that verifies F is a group homomorphism. Okay. So, that means we can use first isomorphism theorem and then immediately conclude that this group that we have, okay, G modulo n modulo the kernel. So, G modulo n modulo the kernel is isomorphic to the image is G modulo H. Okay. So, now we will determine what is the kernel. So, what is the kernel? Kernel is those elements from G modulo n that is mapped to f of xn equal to the identity element inside G modulo H. What it is? It is those xn in G modulo n such that f of xn is equal to xh. Okay, sorry, which is f, sorry, which is h here. The identity element is h, but f of xn is xh, and you are demanding this to be h. That means if and only if x is in h. So that means the kernel of f is those xn in G modulo n such that x is in h. But what it is? It is exactly h modulo n by definition. Okay. So that means we proved h modulo n is normal in G modulo n, and this G modulo n modulo h modulo n is isomorphic to G modulo h. Okay. So in some sense you are allowed to do actually cancellation. This n and n you can cancel, and then you will get G modulo h. So this is I am telling just for the sake of remembering, okay, not for it does not make any sense what is the meaning of cancellation here, but one can reinterpret this like that so that one can remember this. Okay. So basically when you have this kind of tower, okay, you have h and then you have n, both are normal in G. Okay. So then you can look at this G modulo h on the one side, and then you have G modulo n where you have h modulo n. So if you look at the quotient of this, that is isomorphic to this. Okay. So this is something very interesting, because like I said, the second iterative procedure does not give anything new, it gives back to the quotient only. Okay. So now for example, like we can use in various examples and then understand what will happen to the quotient of quotient. For example, let's look at this particular thing. Okay. So we have seen this example. You can see that Z is sitting inside Q, Q is sitting inside R. So with respect to addition, all of them are groups, okay, and ZQ they are all subgroups of R. Since R is abelian, so they are all actually abelian subgroups. So it makes sense to do these quotients R modulo Z and then R modulo Q and then Q modulo Z. Okay, all these groups make sense. So let me write it again. So this is your H, this is your N, and this is your G. Okay. So you can make R modulo Q, and then you can make R modulo Z, and then modulo Q modulo Z. Okay. Basically what we are saying, these two are isomorphic. Okay, we do not get anything new. So similarly, you can work out some details, like for example, you can take 4Z which is contained in 2Z which is contained in Z. Okay. So then again this is N, this is H, and this is G. So then you can make Z modulo 2Z. Okay. So that will be naturally isomorphic to Z modulo 4Z, and then you can go modulo 2Z modulo 4Z. So what it actually tells? So basically if you recall, so Z modulo 4Z, this has 4 elements, okay, because this is a finite group of order 4, it is also a cyclic group. The elements of this is denoted by, let us say, 0 bar, 1 bar, 2 bar and 3 bar. Okay. where I bar is just I plus Z. This is the coset. Okay. So, now that means this 2Z modulo 4Z corresponds to subgroup of Z modulo 4Z. Okay. This 2Z modulo 4Z. So, this corresponds to something inside Z modulo 4Z. So, you can see what it is. Okay. So, basically you take all possible cosets, okay, where the coset representatives are coming from 2Z. So, that means the cosets corresponding to even integers. So, what they are? They are exactly 0 bar, 0 plus 4Z, again 2 bar, 2 plus 4Z. So, 0 plus 4Z and 2 plus 4Z, they corresponding to this 2Z modulo 4Z, this cyclic subgroup of order 2. Okay. So, when you take cyclic subgroup, cyclic group of order 4, and then if you take the quotient of that, which is cyclic subgroup of order 2 inside order 4, then the order of that group will be just 2. Okay. And that again will be cyclic, because the quotient of any cyclic is cyclic. Okay. So, you get order 2 cyclic group on the left side, that is what we are getting here, Z modulo 2Z. Okay. So, this is something you can do in general, not a problem. Okay. So, for example, you can take some devices, let us say DZ, and then sitting inside NZ, which is sitting inside Z. Okay. Where D, N, they are natural numbers, such that let us say D divides N. Sorry, the other way. So, here D, here N. Okay. This is exactly like this, 4, 2 and 1. So, then you can construct the following groups. So, this is your N, this is your H, this is your G. So, if you go G modulo H, which is DZ. So, this is a cyclic group of order D, which is isomorphic to Z modulo this NZ. Okay. So, if you go back, so what is it? It is Z modulo N and H modulo N. So, Z modulo NZ, and then you are going modulo DZ modulo NZ. Okay. So, this actually tells you some interesting fact that we proved already. For example, if you take this Z modulo NZ, which is a cyclic group of order N. Okay. This is cyclic group of order N. Okay. Any cyclic group of order N will be isomorphic to this. So, now what we indeed saying, this DZ modulo NZ is a natural subgroup of this. So, this is a subgroup. Okay. So, now what is this subgroup? What is the order of this subgroup? Okay. So, if you recall what is this Lagrange's theorem. Okay. So, the Lagrange's theorem says the index of the subgroup inside G, okay, that is G colon H, that is the index, that is exactly equal to order of G divided by order of H, okay, for finite groups. So, that means the order of this left side, which is the finite group, cyclic subgroup of order D, Z modulo DZ, that is exactly same as order of the group, order of G and Z, which is N divided by order of DZ NZ. Okay. So, from this you can easily work out what is the order of this particular subgroup. Okay. So, what it is, you can see that this is exactly equal to N divided by this order of DZ divided by NZ. So, that means order of DZ divided by NZ is exactly N by D. Okay. So, you have a natural cyclic subgroup of order n by d inside Z modulo n Z. Okay. So, if you recall, okay, so the generator of this is exactly that n by d plus n Z. Okay. So, this is something I explicitly actually constructed when we were working with the cyclic group, but here I am demonstrating using these isomorphism theorems also. You can see that they are there naturally sitting. Okay. Because this is abstractly proved, now you can use it for any particular cases. Okay. Now, look at another example. Okay. So, let us say something interesting. Okay. Let us say G. So, any finite subgroup we know how it looks like. Okay. This is UN, this is the nth roots of unity. So, this is a subgroup inside S1, which is a subgroup inside C cross. Okay. This is those Z in C cross such that the Z power n is 1. S1 is the unit 1 elements. Okay. So, now you can treat this is capital N, this is capital H and this is capital G. So, then what happens? Then you can see that you can take G modulo H. Okay. So, let me write it, that is C cross modulo S1. Okay. If you remember what it is this is the ray. Okay. It is isomorphic to naturally the 0 comma infinity. So, this is isomorphic to. Okay. So, now you take C cross modulo UN and then you take modulo S1 modulo UN. Okay. So, from our earlier discussion we know this is isomorphic to 0 comma infinity, that R plus. Okay, that is the ray. But this is something looks somewhat complicated. Okay, but we are saying that we are not indeed getting like anything new. Okay. So, if you actually think about it, so this maybe I will leave it as exercise, because this is something I already proved. So, when you take C cross modulo UN, this is isomorphic to again C cross. Okay. Again S1 modulo UN, if you think about it, it is again isomorphic to S1, because when you look at the map, okay, which since Z goes to Z power n, when mod Z is 1, then the image also will land in S1. And when you have this Zn equal to W, okay, when you look for, okay, for W in S1 the solution, then you can see that mod Z power n also will be 1. So, that would imply that mod Z is 1. So, the roots of this equation lie here. Okay, that is why you get this isomorphism. So, even though these very weird looking groups like C cross modulo UN modulo S1 modulo UN, that can be using these isomorphism theorems can be realized to something very well known, and again using isomorphism theorem that can be realized to something again very well known. Okay. So, that is the advantage of having all these isomorphism theorems. So, which actually tells you like how to simplify these quotients, okay, using the known groups. Okay. So, again I would actually leave it to you to actually work it out, some more examples. Okay. I will add it in the assignment sheet. So, for time being I will stop here. Okay. So, from next class I would start actually the group action, okay, group acting on a set, and then we will see some of the examples on the important consequences of group action. Okay, I will stop here. Thank you.